In this lesson, we're going to be finding the complete response of a linear system that is described by its transfer function, h of s, for the case of a sinusoidal input. And we'll begin by actually considering a simpler input, and then follow that with considering the sinusoidal input, which will prove to be a little more involved. So what we're going to assume is that you have some system, we have some system, that is described by a transfer function, and whose input, we'll call it x of t, and the output is y of t. Now, what kind of system could this be? If you're coming from a circuits course, we might be comfortable with something like this. So I'll make up a circuit here. Say Vi is applied over here at the left. There'd be a voltage source. Let me go ahead and draw a voltage source here. We have an R and an L, and maybe the response is the voltage across the inductor. We could also talk about the current I, which happens to be the input current, and the output current. I'll just call it IL. So maybe we have a Vi as an input. We have a VO or an IL as an output, and we're going to describe that by a transfer function. In this case, the transfer function can be found very easily because of the simple network. We'll use impedance to help us do that. So the impedance of an inductor is SL, so ZL of S is equal to SL, and we can use voltage division to find VO as a function of VI. We'll just write that VO is equal to the impedance of the inductor over the impedance of the inductor plus the impedance of the resistor, which is R times VI. And these are functions of S. And this here is the transfer function. Now, if we were solving for IL, so if IL was our output, the system output, then we would have a different transfer function. What would we have in this case? IL, and I'm going to write it in terms of S because we're using impedance, would be equal to the total voltage applied to the system divided by the impedance that voltage sees. So this would be my Z of S here. That impedance is nothing but R plus SL. So in this case, we would have that IL of S is equal to 1 over R plus SL times VI of S. And this would be our transfer function. Maybe I'll call this H1 and I'll call this H2. One thing we notice is that they share the same denominator. Same denominator. And no matter what transfer function you were to write for this system, you would always find the same denominator. As an exercise, so I'll give you a little exercise to try. If I can spell exercise. Exercise. Okay. Find H of S, call it H3 of S, which would be defined as, let's say, V of R of S over VI of S. Okay, so what we're going to do is find, here's VR up here. Express VR of S as H3 of S times VI of S. And what I'm going to claim is that this transfer function is going to be something over R plus SL. And there's really only so many transfer functions you can write for this network or this system because it's a very simple system. But this is something that's a characteristic of linear systems, and that is that no matter what transfer function you express to relate the input to some output, you will always have the same common denominator. And that is because the denominator actually is the characteristic equation of the differential equation that describes that system. And it's invariant over the various outputs that you might be interested in evaluating, right? Each transfer function is allowing you to describe a different state in the system or different output in the system to the input. And that characteristic equation, which comes from the differential equation, is invariant to that. Okay, so draw a line here and we'll return to our task. We have an input x of t and an output y of t and a linear system h of s. So the complete response we'll call that y of t, is made up of two components. There is a first component that is due to the natural response. This is natural or homogeneous. These are all equivalent names. Natural, homogeneous, transient. That's our first component in our complete response, plus our steady state response. So steady state, we might also call it particular. That's what you call it in a differential equations course. We might also call it forced. It's being forced by a particular type of excitation in the input. So we need to find each of these components. And the process is 1, find either the homogeneous or particular. So I'll say find yp, 2, find yh, and this will be having one or more undetermined coefficients. And then 3, satisfy initial conditions using the combined y of t equal to y of h plus y of p, and this will lead to determining or solving for the undetermined coefficients. So this is an important point here in the process, that when you find the particular solution, which is step 1, we can find the exact particular steady state expression. We can quantify it. There are no undetermined coefficients in it. Secondly, when we go to find the homogeneous or transient or natural response, we will find the functional form, like is it an exponential decay, and if so, with what time constant, is it an exponentially decaying sinusoid, then what's the frequency of the sinusoidal decay, and the sinusoid, and what is the time constant. But there are some coefficients that we won't know, and they were related to the amplitudes. So these are called the undetermined coefficients. We don't determine those until we put together yp and yh, forming y of t, the complete response, and then we satisfy the initial conditions, particularly what is the value of y at time 0, or for systems that have that are higher order, that have more than one state, we would be looking not only at y at time 0, but the first derivative of y at time 0, and maybe the second derivative of y at time 0. But in that final third step is where we can determine those undetermined coefficients that showed up in our homogeneous or transient or natural response. And that's when we get to fully describe the complete response. Okay, so let's do this for a simple system. Okay, so let's consider an h of s. Say it's very... We'll just do a first order system. Okay, so we'll say it's h of s is equal to some constant k over 1 plus, and I'll say s times tau. Tau is just a constant that describes it's going to be coming from whatever this system is. I'm not going to describe the system, but it could be could be the circuit above maybe. And so first we're going to find the steady state or particular response. Find y of p. Now we can find the particular solution several ways. We could find it directly from the differential equation of the system, but here in this case the description of the system that we've been given is this transfer function. So we can find it using the transfer function, and that's what I'm going to do here. Y of p of t is going to be equal to, well, it will be a sine if our input, let's consider an x of t, that is equal to, in this case, let's do something simpler. Let's say x of t is equal to just 3 u of t. Okay, so what it means, it's 0 and it steps to a value of 3 at time equal to 0. Okay. So y of p, y sub p I should say, is equal to the transfer function evaluated at s, okay, and this is going to be where s is equal to, and we have to decide that, times x of t. Now, and we're going to solve this for t greater than 0. So just after time 0, what happens? Well, for t just greater than 0, we have x is going to be equal to 3 for all time that's going to be greater than 0. So this is going to be equal to 3. And we can say this is actually 3 times 0 times t, 3 times e to the 0t. In other words, s is equal to 0 in this case. So we're going to evaluate our transfer function at s equal to 0. And now we have this trivial case that y sub p of t is going to be equal to k over 1 plus 0 times 3, or in other words, 3k. So our particular solution is just 3k. Now things get a little more interesting when we do a sinusoidal excitation, and we'll do that here in a moment, but I'm going to finish working through this problem with this simpler excitation first. Second step is find y of h, the homogeneous response. Now the homogeneous response can be found using the transfer function. So found using particularly the poles of h of s. What are the poles? Poles are the zeros, or the roots, of the denominator. And that the denominator is actually called the characteristic, or it turns out to be the characteristic equation. And I have a previous video that talks about that. So, in our case, the denominator, so if we say that h of s is equal to a numerator over a denominator, then we have that the denominator for our transfer function case is just 1 plus s times tau. And we want to find the roots of the denominator. So the roots, which are also called the poles of the transfer function, and of course they're poles because when the denominator, when you plug in a value of s that causes the denominator to go to 0, the transfer function goes to infinity, it explodes. And so if you're plotting that, it looks like a pole, it goes up vertically. That's where that name comes from. So the roots here are going to be just one of them, s is equal to minus 1 over tau. So we can therefore say that the form of the natural response is going to be y sub h of t is equal to some constant a times e to the st, where s is going to be equal to minus 1 over tau. So this will be a e to the minus t over tau. And this is going to be for time greater than or equal to 0. So here is our homogeneous response. Thirdly, we now need to solve for the initial condition. There's only going to be one of them here. So we have that y of t is equal to the particular plus homogeneous response, so that'll be 3k is the particular plus a e to the minus t over tau for the homogeneous. And we're going to check and see what does this evaluate at time 0. It'll evaluate to 3k plus a. Okay, and this must equal the specified initial value, initial condition for y of t. So suppose that we were up here, we also said that y of 0 was equal to minus 2. Okay. Well, then we'd say, well, minus 2, it must be equal to 3k plus a. Therefore, a is equal to minus 2 plus 3k. And we could therefore write our final solution for our complete response. Y of t is equal to 3k minus 2 plus 3k times e to the minus t over tau for t greater than or equal to 0. And we see that this first term is just constant in time, and the second term actually starts out at, what is it going to start out at? It'll actually start out at, the first one is at 3k, the other one is going to be at minus 2 minus 3k, and it will decay to 0. Right? And we add those two together. And that will equal something that will look like this. It'll start at minus 2, and it will eventually go up to 3k. That is our complete response. So notice how we satisfy the initial condition. It starts at -2, but we also arrive at the final steady state response, which we found way up in step 1 to be just 3 times k, where k was that coefficient in the numerator of the transfer function. Okay, now let's repeat this for the case of sinusoidal excitation. So consider y of t is equal to Vn times sine omega t. And again, we're going to have h of s is equal to k over s tau plus 1, and we'll say that y times 0 is equal to, and I'll just say here it's y sub naught to keep it as a variable rather than a number. Okay, so we're going to find the complete response, y of t. Step 1, we're going to find the particular response. And that's going to be equal to, now we might just write, oh, it's h of s times x of t. This is going to be evaluated at s equal to whatever the s value of x of t is. Well, for sinusoids, okay, we have that sine of omega t turns out by Euler's formula to be equal to 1 over 2j, or 2i, the imaginary number, times the quantity e to the j omega t minus e to the minus j omega t. And so we have s values equal to j omega and minus j omega. And we can just plug in the j omega. It turns out you don't need to consider both signs. Okay, now because of plugging in an imaginary s, h of s will now be complex. H of j omega will be complex, meaning it'll be like an a plus jb, and of course these are going to be functions of omega, right? So they're not going to be the same for every frequency, but they will be constants once you choose the omega based on whatever you're exciting with. So the particular solution, I'm not deriving this here, so let's assume that it has been shown in a previous lesson. The particular solution for sinusoidal excitation for a linear system described by the transfer function h of s turns out to be the magnitude of the transfer function evaluated at the omega of the excitation times the magnitude of the input x, which is Vm, times sine omega t, the frequency of the input, but then there will be a phase shift that will be equal to the angle of the transfer function evaluated at j omega. So that's our particular solution. For h of s equal to k over 1 plus s tau, we can find the magnitude of h of j omega is simply going to be equal to the magnitude of k divided by the magnitude of the denominator term, which is going to be 1 squared plus plus omega tau quantity squared. And it won't be j omega quantity squared. It will just be j omega tau quantity squared. It'll just be omega tau quantity squared. Okay, this is a real number. Evaluates to something real, and it'll be positive, right? Even if k is negative, it will be positive. It's simply the magnitude. Secondly, we need the angle of j omega. The angle of h of j omega. The angle of h of j omega will be equal to the angle of k in the numerator minus the angle of the term 1 plus j omega tau. We can't express the angle of k anymore, because if k is positive, the angle will be 0. Maybe I can just write this. It's going to be 0 if k is greater than 0, and it's going to be plus or minus 180. Either will work if k is less than 0, but we don't know what it is. Okay, minus, and then the angle of this term here will be, if I plot this on the imaginary or the complex plane, this is going to be the angle arctan of omega tau over 1. Okay, so therefore we could write the particular solution as absolute value of k over square root of 1 plus quantity omega tau squared times Vm times sine of omega t plus angle of k minus arctan of omega tau. This is our particular solution. Until we have numbers, we can't go any further. But it's sinusoidal. It's sinusoidal, the same frequency as the input, but the output will be attenuated. This will attenuate, right? And this here is going to phase shift the output. Now, secondly, let's find y of h. And here, since y of h is the homogeneous or natural response when the input excitation is turned off, it is exactly the same as what we had before. So it will be equal to a e to the minus t over tau as found previously. Okay, this is not dependent on VI form, functional form. And then lastly, we're going to satisfy initial conditions. So we write y of t is equal to a e to the minus t over tau, that's the homogeneous, plus the particular will be this expression that we derived previously. Okay, and we'll set this to 0, so at time 0 we have this equaling y, capital Y sub naught, which is our initial condition up here, and this will have to equal a plus absolute value of k over 1 plus square root of 1 plus omega tau squared times Vm times sine of the angle of k minus arctan of omega tau. So we can solve for a as being equal to y sub naught minus this big expression. And this gets painful to write out many times. Eventually you plug in a number, but I'm going to go ahead and, or plug in numbers, I'm going to go ahead and write the whole thing out now. One last time, so we have y of t is equal to a, nope, not a, we know what a is now. It's going to be equal to y sub naught minus this whole big expression. Okay, that is a times e to the minus t over tau plus our steady state response. Which is this sine omega t that's phase shifted. Okay, and this is going to be valid for t greater than or equal, oops, not tau, t greater than or equal to 0. Now, what does this look like? I'm not going to attempt to draw it other than to note that the first term is going to be either something that's positive in decaying, sorry, that's supposed to be an exponential decay, or negative. We don't know. This all depends on what a is. This would be if a is greater than 0. Over here would be if a is less than 0. But it's going to eventually go to 0. And the other portion is that we have some sinusoidal response, which is phase shifted. So I don't know where the, where it crosses the zero axis there. Where it crosses the horizontal axis, sorry. But it will be a sinusoid with some phase shift. Okay, so I think I can stop here and make sure that we've covered everything. So what we've done is we've considered finding the complete response of a linear system that's described by its transfer function, and we looked at the case specifically of a sinusoidal excitation. We used the transfer function's magnitude and angle to determine the steady state response, and we used the transfer function's poles, or the roots of its denominator, to find the form of the natural or transient response. And then we put those two together and looked at the initial conditions at time 0, and in doing so we could find the undetermined coefficient of our natural response solution to arrive at a final complete solution that was completely determined by the initial condition, y naught, and by the various parameters of our system, in this case k, tau, Vm, and then omega.